This is kind of a nice property of the protocol. We can also go and investigate the structure of the state space. For this, let's create a fresh page. Just call it state space. Drag it out onto the binder. So we can draw the initial node of the state space. Initial node is always node number 1. We can see this node has a single outgoing state and a single ingoing state. And we can click on this blue expanded triangle to actually see the marking of the state. It contains a bunch of tokens. I can use this tool to show the successors of the state. We see the one successor we expected. And state number 2 is the one where we have transmitted the first package. So we should see here on A we have a single package. I can go and display the successors for this, and I continue doing that, exploring the state space. Now we notice that state 1473 was interesting. So let's try and draw that. Okay, so we can see this certainly has no successors, but how do we actually reach this state? So let's try and draw the predecessors. Okay, we can reach that in a number of ways. So we can try and investigate how do we actually get from the initial state over here to this dead state. Maybe that's not so interesting, so instead we can get the tool to do it for us. So we create an auxiliary text and write in a state space query all nodes in the shortest path from state number 1 to state 1473, the dead state. We can use the simulation tool we didn't use in the simulation section and use this to evaluate this query. So here we get a list of all nodes in an execution from the initial state to the dead state in the shortest execution sequence. So I can use this to go and investigate the error trace in my model if indeed this was an error. Or I can use the draw subgraph tool to automatically draw this part of the state space. So I get all the nodes and I can draw the arcs. A final note is you saw I could click on the blue expander triangle to show a marking. In the same way I can click on an arc to show the binding that leads from one state to another. Now, in the beginning I said that we needed to make this model finite. Well, what happens if we hadn't done that, if we'd actually tried to generate the state space for a model with an infinite state space? Well, let's take a look. Well, CPM tools doesn't handle it and doesn't catch it. It can't distinguish between the case where the state space is infinite and when the state space is just very large. So it just tries to calculate the state space. This is of course not desirable, so it has some options so we can stop the state space calculation. So we go to the Calculate State Space tool and select Set Options. They open down here for some reason. So we can set the number of nodes to maximum. Calculate, when it's set to 0, it means calculate as many nodes as you can. Same for arcs. And we also have one for secs, that means seconds. So the calculation automatically stops after 300 seconds, that's 5 minutes. This is maybe a little long to sit through in a video, so let's put that instead at 10 seconds. And during your experiments I recommend setting this value to a fairly low value, so such as 20 or 30 seconds. Okay, so we have now set a number of seconds. So now the state space calculation will continue for at most 10 seconds. Close the options. So we want to generate the state space. We must remember to rewind back to the initial state because this state has no enabled transition, so the state space will just contain a single node. So let's go back to the initial state and we enter the state space tool again. If you forget, the tool is going to tell you that you need to enter the state space tool. Now we calculate the state space and we can see it takes longer this time. It will take 10 seconds to be exact. And there we go. Now I don't get a green bubble, I get a yellow bubble. Yellow bubble means there was no error, but it didn't complete successfully either. And it basically says that the stop criteria has been satisfied. We have calculated the state space for 10 seconds. Okay, We could continue calculating the state space, but let's instead calculate the SCC graph and generate the state space report to investigate what actually happened. We just overwrite the old report. So now we have calculated 6,000 nodes, we have used 10 seconds, and we have only calculated a partial state space. Okay, this is the first indication that something is wrong. The next indication is when we go and look at the bounds. Well, the integer bound says we have 18 tokens on this place. When we have a very large upper bound on the number of tokens, or a very large multiset upper bound, this is an indication that we may have a problem in our model. Continued calculation will show that this upper bound just increases and increases and give us a hint to what is the problem. If I said that the tool was allowed to calculate for the entire 5 minutes, it would have just done so, and I'd just get larger bounds down here. So I might not have gotten more useful information. But I've seen that I could use the state space report to get some insight into the model. I've seen that there is only a single dead state where no transition can be executed. You've also seen that this is indeed a home marking, so we can always reach it. And in order to avoid reaching that state, we have to continuously executing the send packet and transmit packet transitions, meaning that the only way for the protocol to complete unsuccessfully is if we continue losing packets. So thank you for your attention. I have no immediate plan on a part 6 of this small tutorial, but who knows what the future brings.